So in this video, we're going to do 6 practice problems. Here they are listed out just in case you want to take a sneak peek and kind of plan on your page. The first 2 right here are going to be just plain normal Lewis structures. This one right here has boron, so that's going to be the example of the incomplete octet. And then these last 2 right here, which have xenon and phosphorus, both larger elements, are going to be examples of the expanded octet. Okay, so we're going to do the first example, SOCl2. So do me a favor and lay your notebook out so you can see the steps as we're going through this. So step number 1 is to determine the total number of valence electrons. To do this, we look at their placement on the periodic table, and we know that sulfur has 6, oxygen also has 6, and each chlorine is going to have 7, so that's a total of 14. So that means in total we have here 6, 6, and 14, so that is 26. And there's no charge, so it's just straight 26. What I do then is I take those 26 electrons and I write them over here, and I call that my electron bank. So this is just like the pile of bingo chips that we put over to the side. Now we're writing 26 over there. Step number 2, write the skeleton structure of the molecule. So this is where we lay it out and we tend towards symmetry, just like nature, and try and find a nice pretty pattern for these guys. Okay, and for this one, it looks like sulfur is the least electronegative because it's farther down and farther to the left than both of them. So it's going to be our central atom, so let's write that one. And then to get symmetry, we'll put our oxygen up there and our chlorines on either side of the sulfur. That looks good. Now, a skeleton structure does not stop here. Now we need to connect those. So obviously they're going to be bonded to each other, so we just put a single line to represent the bonds. So we've connected those guys, created a symmetrical model. And what we've done to do that is we've used a single bond between all of the elements. So that's 2, 4, 6 electrons that we've used so far. So we're going to come up here to our bank, and we're going to subtract 6 electrons from it. And so that leaves us with 20 electrons that have not been placed yet. So that means if we're sitting in class, we've put 6 bingo chips right there. So we've taken 6 out of our pile. We're left with 20. Now we're going to take those 20 and distribute them out here to try and create our structure. So I'm going to start with sulfur and put 2 valence electrons right there. So that's 2 that I have used. So that's going to leave us with 18. I'm going to move over to the chlorines now. So each of them is going to need 6 more. They've only got 2 from that bond. Okay, so that's a total of 12 electrons that I have used so far. And now I have 6 electrons left over. So now before I go throw dots down, let's make sure that we have enough to finish up this. So sulfur, or oxygen, I'm sorry, has 1 single bond. So it has 2 electrons. Looks like it's going to need 6 electrons as well, which is great because we have 6 electrons left in the bank. And so that is going to mean that we are left with 0. So just like in class, you didn't want any bingo chips left over to the side. You never want any electrons left in your bank. You want to make sure that you always balance out to 0. So in this case, everyone's got their 8 valence electrons, and we have 0 in the bank. This, ladies and gentlemen, is a complete Lewis structure. Okay, that was a nice simple one to start out. Make sure that you're following the steps and running along your bank over to the side. All right, here's another one. Let's move through a little bit quicker on this guy, since hopefully we're kind of getting the hang of it. Let's count up our total number of valence electrons. 1 from each hydrogen, 4 from the carbon, 6 from the sulfur. It'll give us a grand total of 12 valence electrons. That skeleton structure tending towards symmetry. Carbon is going to be our central atom, since it is going to be the least electronegative. And then we'll put hydrogen on either side. And then we'll throw that sulfur up here. And right now it looks like I've got 6 electrons out there, so I'm going to take 6 electrons away from the bank, and we're left with 6. Before we get crack-a-lack-and laying down the last valence electrons, let's count to make sure that we have enough. So carbon here has 2, 4, 6, so it looks like it needs 2 more. Sulfur here has 2, so it needs 2, 4, 6 more. So we've got 2 there and 8 there that we need. We've only got 6 left in our bank. That's not enough. And so on our thing we wrote down if we have too few on step number 4, we need to do multiple bonds instead. So we know that hydrogen cannot form any more than a single bond, so we're not going to be able to form a double bond or a triple bond with hydrogen. It's going to happen between the carbon and the sulfur. And so in this case, let's go ahead and put down a double bond, which represents 2 electrons. So I'm going to take 2 electrons from the bank, and that leaves us with 4 electrons left. And so at this point, carbon has 2, 4, 6, 8, so carbon's good. Sulfur only has 2, 4, so it needs 4 more. And what do you know? We have 4 left in our bank. So by doing that double bond, we made it so that now we can have a complete octet on everybody. Let's subtract those 4 final electrons, making sure that we balance out to 0. Next, let's take a look at BH3. So boron has 3 valence electrons, and then we've got 3 hydrogens. So that gives us a total of 6 valence electrons. And let's lay out our skeleton structure. So step 1 and step 2, we would have boron attached with 3 hydrogens. And so that's 2, 4, 6 electrons. Subtract 6 electrons from the bank. Oh, that was easy. Now we've got 0. But wait a minute. Boron here only has 2, 4, 6 valence electrons. That doesn't satisfy the octet rule. But wait, I remember now. One of the exceptions to the octet rule, called the incomplete octet, was boron. Boron only needs 6 valence electrons, which it's got right here. So what do you know? That one's done. Next is xenon difluoride. So some of you might be jumping at this and saying, hey, xenon's a noble gas. It doesn't form bonds. Actually, yeah, it can. The larger noble gases, especially krypton and xenon, can both form bonds. They don't like to do it, but they will to help out their comrades who need a couple extra valence electrons. But more often than not, whenever you see them, it means it's going to be an expanded octet problem. So in this case, let's do step number 1, determine our total number of valence electrons. We've got the 8 from the xenon, the 14 from the fluorines, and so that's a total of 22 electrons in our bank. And if we set up a skeleton, so that's xenon bonded to fluorine, which is bonded to fluorine. At this point, we have 4 electrons out there, so we can take away 4 electrons, and that leaves us with 18 more electrons to distribute. So let's complete the octet on xenon. It's going to need 4 more to get the octet. So you subtract those 4, we're left with 14 electrons. Now let's do it to fluorine. Each fluorine is going to need 6 more. So that's 6. That means we've put out 12 electrons. Now you might be tempted to stop here, but check this out. We're left with 2 more electrons. So even though we have satisfied the octet on all of the atoms involved, there's still extra electrons. So on step number 4, if we have too many, what happens? Expanded octet. So if you look at expanded octet, that means the extra electrons are placed as lone pairs on the central atom. So xenon here, yeah, xenon's got 8 valence electrons, but it's a big guy. It can handle a couple more. And so it's actually going to have those extra 2 electrons slapped right there on it. And so then we take off those 2 electrons, and now we are left with 0. This is a prime example of why it's important to follow the steps. You probably wouldn't catch that extra lone pair right there if you did not go through and use the bank and make sure that it balanced out to 0. And last but not least, PCl5. Now, this one right here is quite clearly an expanded octet problem. The reason it's an expanded octet problem, the way we recognize it as one, is because we've got phosphorus bonded to 5 chlorines. So right off the bat, phosphorus already has 2, 4, 6, 8, 10 valence electrons. But we're jumping ahead of ourselves. Total number of valence electrons from this guy, it's going to be quite a few of them because we've got quite a few bigger elements, and it's going to be 42 electrons that we need to distribute out there. And already we've got 10 electrons that have been placed, so we can subtract those 10, and that leaves us with 32 more electrons. Phosphorus, looks like phosphorus is good. We need to go and complete the octets on all of those chlorines then. It looks like each of them have 2, so 6 more. And at this point, you need to count carefully how many electrons did we just put out there on the chlorines. We did not put 32, we put 30 electrons out there, which means there's 2 electrons left over. So not only does phosphorus get 10 electrons from its bonded chlorine, there's 2 left over, and they always go onto the central atom. So we're going to put those extra 2 electrons right there to balance out to 0. All right, that's it, ladies and gentlemen. That is how to draw Lewis structures. Biggest advice I can give you is 2 things. Number 1, make sure you follow the steps. Tip number 2 is always use a pencil with an eraser when you're doing these problems.